Okay, class, welcome back. Today we are going to cover how atoms of the same element can have different masses, along with a technique in which proves this concept. If I could summarize our goal up into one thing today, I would say that it would be that we would be able to explain the quantitative relationship between the mass spectrum of an element and the masses of the element's isotopes. And saying that, let's dive into our lesson for today. An atom is composed of protons and neutrons in the nucleus and electrons that float around in the electron cloud. All atoms of a specific element have the same number of protons, but they can vary in the amount of neutrons present within the nucleus. For example, carbon always has 6 protons, but depending on what type of carbon it is, it can have 6 or even 7 neutrons. When two atoms of the same element have differing amounts of neutrons, we call them isotopes. Because the mass number of an atom is calculated by the weight of the protons and neutrons within the nucleus, isotopes have different mass numbers from each other. For example, our carbon atom from earlier can either have 6 or 7 neutrons. If we add those to the number of protons, then our carbon isotopes that we would have would weigh 12 atomic mass units or 13 atomic mass units. In other words, this is going to be carbon 12 or carbon 13. Since there are usually many isotopes of a single element, it can be confusing to know what type of isotope a chemist has without extensive experimentation. Because of this, chemists use the average atomic mass to generalize the calculations with these elements. The average atomic mass is the atomic mass of each isotope of a particular element relative to the abundance of that isotope. So if we're going to calculate the average atomic mass for chlorine, who has 2 isotopes, chlorine-35 and chlorine-37, we would take each of the isotopes and multiply them by the percent abundance. Then we would add those two quantities together. So the percent abundance of chlorine-35 is 75.76%, and chlorine-37 has a relative abundance of 24.24%. We take the mass of our isotopes and multiply them by the percents. So 35 multiplied by 0.7576, which is 75.76% in decimal form. And then we would also take 37 times 0.2424, and we would get 26.516 for chlorine-35 and 8.9688 for chlorine-37. Now we add our two quotients up and get 35.4848, which is extremely close to the average atomic mass stated on our periodic table. This means our calculations are right, and the measurements on the mass of the isotopes, or percent abundance stated, are within an acceptable percent of error. Going back to our relative abundance, or relative percent abundance of an isotope, how do we figure out the specific percent abundance of a sample of an element? In other words, how do we know for certain that out of all the chlorine atoms on this earth, 75.76% of the chlorine atoms are chlorine-35? Or chlorine atoms with 17 protons and 18 neutrons. This percent abundance of any isotope can be determined experimentally by a technique called mass spectrometry. In mass spectrometry, a sample of an atom or molecule is inserted and put into an instrument called a mass spectrometer. This sample is usually in the liquid state in an aqueous or organic solution. Once the sample is inside the machine, it is heated until it vaporizes. It is then bombarded with high-energy electrons, which knock electrons off the sample, creating cations, or positively charged ions. These cations travel through a magnetic field which deflects the ions down the machine to a plate in which detects the speed and time it takes for the cation to hit it. Well, how does this help us determine the percent abundance of an isotope within the sample? Think about it this way. The speed in which the ion is deflected by the magnetic field is dependent both on the size and charge. If an atom is moving faster than another down the mass spectrometer, then it is lighter than the other atoms, just like you can throw a baseball faster than you can throw a shot put. Additionally, the magnetic field deflects atoms in which have a higher charge down the mass spectrometer faster and aids in further distinguishing isotopes of a particular atom from another. When these ions and isotopes reach the end of the machine and hit the plate detector, the detector is going to make 2 readings. The first is the mass to charge ratio for each of these ions that hit the detector, and the second being the quantity of each of these specific types of mass to charge ratio atoms. With this information, the mass spectrometer will create a graph for the relative abundance of each mass to charge ratio, which looks like this. This chart tells us the percent abundance of each isotope of that element within the sample. Through many uses of this machine, chemists have been able to determine the percent abundance of each isotope within an atom with a high level of accuracy. Well, there you go. Today you learned about isotopes, how to calculate the average atomic mass, and how mass spectrometers work. I think this is going to be the topic in which we stop on today. I hope you learned something new and keep up the good work in this class. See you next time.